let's do a few examples. Some other ones you can try from the textbook I would recommend are from chapter 30, numbers 31, 33, and 71. You can look up your answers in the back of the book. I don't think they're too tough for you to do on your own, but reach out to me if you can't get it solved. So in this example, an LC circuit has a 10 milliohm inductor. The current has its maximum value of 0.6 amps, and this happens at t equals 0. A short time later, the capacitor reaches its maximum potential difference of 60 volts. What is the value of the capacitance? So I picked this problem because it introduces the idea of potential difference, and we didn't talk about that in our workbooks. Let's make a list of the things that we know. So we know that in our circuit, the inductor has an inductance of 10 milliohms. 10 times 10 to the minus 3, I said milliohms, millihenries. 10 times 10 to the minus 3 henries. The maximum value of current is 0.6 amps. That's I0 in our notation. A little while later, the maximum potential difference is 60 volts. Delta V, I'm going to write maximum on here so we don't forget that that's the biggest. And we're asking for what is the value of the capacitance? What is C? So let's start with the idea of C, and what do we know about C? Well, capacitance is defined as the charge on the plate divided by the potential across the plates. If we know the maximum potential, we would know that that would go with maximum charge. So capacitance can be the maximum charge divided by the maximum potential. So that's sure true. Could we sort out what QO is? Can we figure out what the maximum charge is? Well, we do know the maximum current. Let's see how that comes into play. So maximum current is omega times Q naught. We found that out as we found the expression for current. Omega is the natural frequency of the system. That's 1 over the square root of LC. So our current is 1 over root LC times QO. So if we want to find QO, we can just solve this for QO. QO equals IO times square root of LC. So now we're pretty good to go. If we want our capacitance, we put in this for our QO, divide by our potential, and we can find our capacitance. So let's get going with that guy. So C is QO over delta V maximum. QO is IO square root of L times C over delta V max. If we want to get rid of our square root sign here, we can square both sides. So C squared is equal to I0 squared. L times C divided by delta V maximum squared. We've got a C on either side, or we've got C squared here and C here. Divide both sides by C, and that's what we get for our capacitance. So C is equal to I0 squared, 0.60 amps squared, times the inductance, 10 times 10 to the minus 3 henries, divided by our potential squared. That maximum potential was 60 volts. Put all that through the calculator, and we get 1 times 10 to the minus 6 farads. Or if you wanted microfarads, you could say 1 microfarad. So there's the capacitance in that circuit. So that's something you could totally measure. For our next example, let's say that for your final exam in electronics, you're asked to build an LC circuit that oscillates at 10 kilohertz. So this is giving you the natural frequency. The maximum current has to be 0.1 amps, and the total amount of energy to store in the capacitor has to be 1 times 10 to the minus 5 joules. What inductance and capacitance do you have to use in order to get this? Okay, let's start with a list of the things that we know, and let's think about where these things are going to take us. The frequency is 10 kilohertz, or 10 times 10 to the 3 hertz. Places we're probably going to want to go with this is we know that omega is 2 pi f. We also know that omega is the square root of 1 over LC. So there's a couple of things we're going to use. The maximum current, I0, is equal to 0.10 amps. what we might do with this is remember that I0 is omega times Q0. So maximum current is frequency times charge. We know that our maximum energy, I'm going to call that E maximum, is, and it's stored energy, so it's going to be a potential energy, 1 times 10 to the minus 5 joules. What we're trying to find is what is the inductance and what is the capacitance. So let's think about what to do with this energy. To get an idea of the energy, let's just go back to springs for a second. If we have a mass oscillating on a spring, it goes up and down. When it's at the equilibrium, it's going its fastest. All of the energy is kinetic energy. So the total energy is your K maximum, which is a half times m times V maximum squared. When it's out at the amplitude, that's when it's turning around. So it stops instantaneously and turns. Out at the amplitude is where it has its maximum potential energy, which is a half times K times A squared. And somewhere in the middle, it has a little kinetic and a little potential. In an LC circuit, the same deal happens. So in an LC circuit, and we talked about this when we introduced it, in an LC circuit, energy can be all stored in the electric field, all stored in the magnetic field, or a combination of both. So energy can be U maximum of the magnetic field for the inductor, or it could be U maximum of the electric field in the capacitor. Or it could be a mix of either. So we can calculate the maximum stored potential energy in the inductor, we could calculate the maximum stored energy in the electric field, and either of those two things would have to give us the total maximum energy, 1 times 10 to the minus 5 joules. So let's say that our maximum energy is equal to the mu max stored in the magnetic field of an inductor. So the energy, so the max energy stored in the inductor. This is an expression we did in our last section, equals U maximum. And we know that that expression is a half times the inductance times the maximum current squared. We could also do the capacitor, a half CV squared, but we don't have enough information for that, so let's do the maximum of the inductor. That means we can find our inductance. So L is equal to 2 times the maximum energy stored divided by the current squared, the maximum current squared. So that's 2 times the maximum energy altogether, because the most you can have in the inductor is the most you can have. I maximum is what we call I0, so we have 2 times the energy, 1 times 10 to the minus 5 joules, divided by the maximum current squared, 0.10 amps squared, gives us an inductance of 0.0020 henries, or 2 millihenries. Okay, there's our inductance. We also want the capacitance. So let's go back to this idea of I0. I0 is omega times Q, or let's go back to our omega. We know the frequency, so we know omega, and omega is root 1 over LC. So let's use that approach. Okay, so we want to find the capacitance next. So we know that omega is equal to 2 pi f, and we know that omega is the square root of 1 over LC. So if we want to find our capacitance, let's square both sides. 4 pi squared f squared equals 1 over LC. Let's solve for C. C equals 1 over L times 4 pi squared f squared. We put in our numbers. 1 over. L is 0.002 henries times 4 times pi squared. Frequency was 10 times 10 to the 3 hertz. and that frequency has to be squared. Put that through the calculator and we get 1.27 times 10 to the minus 7 farads, or 0.127 microfarads. Okay, so for that exam, these are the inductors and the capacitors we'd have to use. Next, we'll do an example that's mathematically easy but conceptually maybe a little bit hard.